force on a current-carrying conductor. We know that a current-carrying conductor produces a magnetic field around it. In case of a straight current-carrying conducting wire, the directions of the magnetic field lines are in the form of concentric circles with the conductor as center lying in a plane perpendicular to the straight conductor. The direction of magnetic field can be obtained by Maxwell's right-hand grip rule or right-hand screw rule. For a very long straight conducting wire carrying current I, the magnetic field at a perpendicular distance r from the straight wire is mu0 upon 4 pi times the ratio of the magnitude of the current and the shortest distance from the wire. Here, proportionality constant mu0 upon 4 pi is equal to 10 to power minus 7 Tesla meter per ampere. In case of a current-carrying circular coil, the directions of the magnetic field lines are concentric circles near the wire and almost straight near the center of the coil. If the current through the circular coil flows in anti-clockwise direction, the direction of magnetic field at the center of the circular loop is perpendicular to the plane of the coil directed outwards. On the other hand, if the current flows in clockwise direction, the direction of the magnetic field at the center of the circular loop is again perpendicular to the plane of the coil but directed inwards. The direction of magnetic field at the center of circular coil is given by right-hand grip rule. For a circular coil of radius r carrying current I, magnetic field at the center of the coil is mu0 times the ratio of the magnitude of the current and the diameter of the coil. Experimentally, Ørsted has shown that a current-carrying wire exerts a force on a magnetic needle and deflects it from its usual north-south position. French scientist André Marie Ampère suggested that a magnet must also exert an equal and opposite force on the current-carrying conductor. If a conductor is placed in a uniform external magnetic field in such a way that the two magnetic fields, that is, external magnetic field and the magnetic field developed due to the current-carrying conductor, are not oriented in the same direction, then the magnetic fields interact with each other. In other words, this interaction causes a force on the conductor. This indicates that a current-carrying conductor, when placed in an external uniform magnetic field in a direction other than the direction of the magnetic field, experiences a magnetic force. However, the interaction of two magnetic fields produces a resultant field called catapult field. For more clarity, let's see an activity. Take a small aluminium rod and connect it in series to a battery, a key, an ammeter and a rheostat. Suspend it horizontally and place a U-shaped magnet vertically so that the magnetic field remains directly upwards. It can be seen that when the current is allowed to pass through the rod, it gets displaced. If we repeat the activity by increasing the amount of current, the rod is again displaced in the same direction but more quickly. This activity shows that the magnitude of the force acting on current-carrying conductor placed in a uniform external magnetic field is directly proportional to the strength of the current through the conductor. Let's repeat the activity by replacing the U-shaped magnet by a more strong magnet. Now the rod is displaced more quickly. This shows that the magnitude of the force is directly proportional to the strength of the magnetic field. We further repeat the activity by increasing the length of the rod within the magnetic field. This can be done by using a wider magnet. It can be noticed that the magnetic force on the conductor is also increased, which shows that the magnitude of the force is directly proportional to the length of the conductor within the magnetic field. Since force is a vector quantity, so it has direction also. To analyze the direction of force, let's repeat the previous activity by changing the direction of current. The rod is displaced but in reverse direction. If we repeat the activity by changing the direction of magnetic field, the rod is again displaced in the reverse direction. This shows that the direction of the force changes with the change in the direction of current or the direction of magnetic field. It can be observed that when the linear current carrying conductor is placed parallel or anti-parallel to the direction of magnetic field, that is, the current through the conductor is either in the direction of the magnetic field or in the opposite direction of the field, in both the situations, the conductor experiences no force. But if conductor is placed perpendicular to the direction of magnetic field, it experiences maximum force. Furthermore, if the linear current carrying conductor is placed at an angle, say theta, with the direction of magnetic field, the magnitude of the force is found to be directly proportional to the sine of the angle between the direction of current and that of the magnetic field. On combining the obtained observations, the magnitude of the force acting on a current-carrying conductor placed in a uniform external magnetic field is directly proportional to the strength of the electric current, strength of the magnetic field, the length of the conductor within the magnetic field, and the sine of the angle between the direction of current and that of the magnetic field. Experimentally, it has been found that the proportionality constant is 1 for SI units, and the magnitude of the maximum force experienced by the current-carrying conductor placed in a uniform external magnetic field is the product of the strength of the electric current, strength of the magnetic field, and the length of the conductor within the magnetic field. Since the SI unit of force is Newton, thereby the SI unit for magnetic field comes out to be Newton per ampere per meter. It is also referred to as Tesla. The direction of maximum force experienced by the current-carrying conductor placed in a uniform external magnetic field can be obtained by Fleming's left-hand rule. according to which, if we stretch the thumb, forefinger and the second finger of a left hand perpendicular to each other, such that the second finger is pointing in the direction of the current, forefinger is pointing in the direction of the magnetic field, then the thumb represents the direction of force, which is perpendicular to the direction of current as well as the direction of the magnetic field. Here, it can be noticed that all the three quantities, that is current, magnetic field and the force, are perpendicular to each other. Here it should be noticed that this deflecting force is different from other forces, such as the force of gravitation between masses, the electrostatic force between charges, and the force between magnetic poles. Let us see one more activity. Take a thick copper wire and suspend it vertically from a support by means of a flexible joint. Keep the lower end of the wire inside a trough filled with mercury. Because of this, lower end of the wire is free to move in mercury. Connect the positive terminal of the battery to the upper end of the copper wire and connect the negative terminal to the lower end by dipping the connection wire in mercury to complete the circuit. Place a U-shaped strong magnet in such a way that the direction of magnetic field remains horizontal, so that the direction of the current and the magnetic field becomes perpendicular to each other. When the key is closed, the current flows through the wire in the downward direction, and it can be seen the wire is kicked in the forward direction. Further, if we reverse the direction of current, that is, the current flows through the wire in the upward direction, it can be seen the wire is kicked in the backward direction. Till now, we know that a current-carrying conductor creates a magnetic field, as well as current-carrying conductor experiences magnetic force when placed in a magnetic field. When two current-carrying conductors are placed close to each other, they will also experience some magnetic force due to each other. Let us consider two long straight conductors, C1D1 and C2D2, held parallel to each other, carrying current in the same direction. We know that the magnetic field is produced due to current through each conductor. According to right-hand rule, the direction of magnetic field due to conductor C1D1 is perpendicular to plane and directed inwards. Since the conductor C2D2 lies in its magnetic field, therefore C2D2 will experience a magnetic force. According to Fleming's left-hand rule, force on conductor C2D2 acts towards the conductor C1D1. Similarly, the direction of magnetic field due to conductor C2D2 is perpendicular to plane and directed outwards, and the force experienced by C1D1 will be towards the conductor C2D2. That is, both the conductors attract each other. The same can be observed when two metallic wires are suspended vertically, parallel to each other, with their lower ends kept inside the mercury trough and their upper ends are connected to positive terminal of a battery and lower ends with the negative terminal by dipping the connection wire in the mercury. If the current in conductors C1D1 and C2D2 is in opposite directions, the conductors repel each other with the same force. The same can be observed when two metallic wires are suspended vertically, parallel to each other, with their lower ends kept inside the mercury trough. Do you know the same principle is used to launch rockets? We know that a current-carrying conductor, when placed in an external magnetic field in a direction other than the direction of the magnetic field, experiences a magnetic force. We also know that the current in a conductor is due to the flow of charges. Thereby, when a charged particle moves in a magnetic field, it experiences a magnetic force. Electromagnetic induction. We know that if electrical current is flowing in a conductor, there is an associated magnetic field created around the conductor. In a similar way, if we move a magnet near a conducting wire, there should be an electrical current that will be generated in the wire. The phenomenon by virtue of which an electric current is induced in a conductor due to changing magnetic field is called electromagnetic induction. It is an extremely useful phenomenon with a wide variety of applications and used in power generation and power transmission. In 1831, British scientist Michael Faraday and American scientist Joseph Henry introduced the concept of electromagnetic induction individually. But the credit of the discovery of electromagnetic induction goes to Faraday, because Faraday performed numerous experiments to prove that electricity could be generated from magnetism. He not only had clearly demonstrated the phenomenon of electromagnetic induction, but also had developed a good understanding of the processes involved. He hypothesized that whenever there is a change in the magnetic field lines linked with a conductor, an electric current is induced in the conductor, and the current is called induced current. In his experiment, Faraday took a permanent magnet and a galvanometer connected to the two ends of a coil of copper wire. He observed when a bar magnet is moved back and forth inside the coil, there is a deflection in the galvanometer that indicates a current is produced in the coil, and no deflection of the galvanometer is seen when a bar magnet is stationary. That is, a moving magnetic field is necessary for electromagnetic induction to occur. Do you know the cause of the induced current in the coil? The basic cause of electric current is the potential difference or the electromotive force across the conductor. Due to the motion of the magnet with respect to the coil, an electromotive force is developed between the ends of the conductor. Thereby, an electric current is induced in the conductor. In general, whenever a coil of conducting wire is placed inside a magnetic field, a magnetic flux is linked with the coil. When the magnetic flux linked with the coil is changed, an electric current starts flowing in the coil. The current and the electromotive force so produced are called induced current and induced electromotive force, or induced potential difference respectively. Magnetic flux is a general term associated with a magnetic field that is bound by a certain area. It is linked with a surface when held in a magnetic field and defined as the number of magnetic field lines crossing the surface. In general, magnetic flux is the product of the magnetic field and the area through which the magnetic field passes. It has maximum value when the magnetic field lines are normal to the surface and has a minimum value when the magnetic field lines are parallel to the surface. In SI units, the unit of magnetic flux is Weber, which is equal to 1 Tesla meter square. Do you have any idea how we can change the flux over a period of time? Magnetic flux can be changed by moving either the magnet or the conductor away or towards the other. In other words, if there is a relative motion between the conductor and the magnet. It can also be changed by increasing or decreasing the area. Another way to change the magnetic flux is by changing the orientation of the magnetic field. This is generally done by rotating the conducting wire along an axis that is perpendicular to the field. Let's see two different cases of the Faraday's experiment for the electromagnetic induction. In the first case, the coil is stationary and the bar magnet is in motion, while in the second case, the bar magnet is stationary and the coil is in motion. In a closed circuit containing a coil of copper wire connected with a galvanometer, when the north pole of a bar magnet is approaching towards the coil, the galvanometer suddenly deflects in one direction. This shows that some current is induced in the coil. When the magnet remains stationary, there is no deflection in the galvanometer, indicating no induced current in the coil. On the other hand, when the north pole of a bar magnet is moved away from the coil, the galvanometer again shows a sudden deflection but in the opposite direction. Similarly, when the south pole of the bar magnet is moved towards the coil, the galvanometer shows a sudden deflection but in the opposite directions to that when the north pole is moved. The similar effect can be seen when the south pole facing the coil is moved away from the coil. Let us see another situation in which the magnet remains stationary while the coil moves back and forth. When the coil is approaching towards the magnet, the galvanometer suddenly deflects in one direction. This shows that some current is induced in the coil, and the deflection decreases to zero as the coil moves away from the magnet in the same direction. Now, if the coil is moved towards the magnet from the other end, this time the galvanometer shows a deflection but in opposite direction. In this activity, deflection is produced in the galvanometer only when the coil is moved towards or away from the magnet. In these activities, galvanometer showed deflections but in different order. Do you know why? When the magnet is approaching the coil, the magnetic flux or the number of magnetic lines passing through the coil increases, and thereby current is induced in the circuit. When both the coil and the magnet are stationary, there is no change in the magnetic flux and thereby no deflection in the galvanometer. On the other hand, when the magnet is moving away from the coil, galvanometer shows a deflection in opposite direction because in this situation, current is induced in the coil by virtue of decrease in the magnetic flux. Let us see the case of electromagnetic induction due to change in area. When the coil is approaching towards a magnetic field, the magnetic flux linked with its cross-sectional area increases and thereby current is induced in circuit. On the other hand, when the coil is moved entirely inside the magnetic field, the magnetic flux linked with its cross-sectional area does not change. Due to this, no induced current is produced in the coil and the galvanometer does not show any deflection. However, when the coil is further moved, the area of the coil inside the magnetic field goes on decreasing. In other words, the magnetic flux linked with the coil goes on decreasing. As a result, the induced current flows through the coil and the galvanometer shows a deflection but in opposite direction. This activity shows that the magnitude of the induced electromotive force depends upon the magnitude of the magnetic flux, which is the product of magnetic field strength and the swapped area. Faraday also showed that more rapid movement of the coil gives more deflection in the galvanometer. This activity shows that the magnitude of the induced electromotive force depends upon the rate of swapped area or rate of relative motion. On combining the obtained observations, the magnitude of the induced electromotive force, that is the induced potential difference, is directly proportional to the strength of the magnetic field and the rate of area swapped in the magnetic field. This is also equal to the rate of change of magnetic flux. Magnitude of induced electromotive force also depends on the number of turns in the coil. If the number of turns increases, then the induced electromotive force also increases. The results of Faraday's experiments on electromagnetic induction are known as Faraday's laws of electromagnetic induction. These laws are stated as 1. Whenever magnetic flux linked with a circuit, that is a loop of wire or a coil or an electric circuit in general, changes, an electromotive force, that is potential difference, is induced. The induced electromotive force lasts as long as the change in the magnetic flux continues, and the magnitude of the induced electromotive force is directly proportional to the rate of change of the magnetic flux linked with the circuit. The direction of induced electromotive force can be obtained by Lenz's law and the Fleming's right-hand rule. According to the Lenz's law, the induced current produced in a circuit always flows in such a direction that it opposes the change or the cause that produces it. When a bar magnet is moved from left to right towards the coil, an induced current is produced in the coil which opposes the motion of the bar magnet. It will happen so if the induced current in the coil also produces magnetic field lines from left to right, that is, the induced current flows through the coil in clockwise direction when seen from left. Similarly, when the bar magnet is moved away from the coil, the induced current will flow in anti-clockwise direction when seen from left. According to Fleming's right-hand rule, if we stretch the thumb, forefinger and the second finger of a right hand perpendicular to each other, such that the forefinger is pointing in the direction of the magnetic field, the thumb is pointing in the direction of motion, then the second finger represents the direction of induced current, which is perpendicular to the direction of motion as well as the direction of the magnetic field. Phenomenon of electromagnetic induction has many applications. One of them is power transmission, for which transformers are used. It consists of two sets of insulated coils on the two sides of a soft iron core. An input voltage is supplied to one of the coils called a primary coil. The output is drawn from the second coil called the secondary coil. On applying an input voltage to the primary coil, the electric energy is transferred to the secondary coil through the changing magnetic field. Now, if the number of turns in the secondary coil is less than the primary coil, the output voltage is also less than the input voltage. It is now called a step-down transformer. On the other hand, if the number of turns in the secondary coil is more than the primary coil, the output voltage is more than the input voltage. In this condition, it is called a step-up transformer. In general, a transformer works to convert between two voltages and two currents. It can be seen as a converter of one power pack into a different power pack with desired voltage and current ratings. Transformers are widely used for distribution of electrical power from power stations. A step-up transformer is used before transmission through cables in order to reduce the energy loss in the form of heat. Then, at the substations, a step-down transformer is used to make it suitable to the consumers. Here, it should be noticed that the transformer is used to change the voltage of the alternating current only. Do you have any idea of alternating current? We will discuss it in the next class.